That's awesome. Wait, so you have people groundwork? Oh, so you did the software engineering?
I did the software.
You wanted the software.
I'm the bad software engineer.
Do you mind if I'm sitting in front of you?
That's
What am I called?
And so today we have Janni Yuval, who is a visiting scientist at Google Research, and he's now helping developing like a hybrid model of like weather and climate. He has a research background like in like climate dynamics, and also has like a master's degree in subject matter of physics from Weizmann Institute. And today he's going to introduce like neural general circulation model for weather and climate, which is very exciting. And okay, so without further ado, Janni, it's all yours.
Thank you. Can you see my monitor?
Yes, we can see a monitor fine.
Perfect. So I can't see you. So if somebody raises hand, I cannot see it. So
I can help you monitor, yeah, if there is any question. Yeah.
So thanks for the introduction. I'll talk today about neural general circulation models for weather and climate. And I'll start with just like brief acknowledgement to a big group of people who helped here from various institutions. I mean, the core group is at Google Research, which is kind of the first row here, and Stefan. And yeah, so the talk I'll start with an introduction, starting talking about like how machine learning has kind of transforming weather prediction. And I'll talk about also hybrid models and what they are. And later I'll introduce the results. So to give you some context why we have done this work, we'll start with like just a few observations. So in recent decades, you can see this shows you the skill of weather forecasting in the y-axis versus the year. And broadly speaking, if you see the trends going upwards, meaning that our forecast is improving. And this basically is happening due to better and better general circulation models and better numerical weather prediction schemes, essentially. And numerical weather prediction is including a few steps. Today I'm going to focus on one step, which we call the forward model or general circulation model. But basically, it's a combination of a few steps from data assimilation and post-processing. But the question I want to discuss today is whether machine learning or hybrid models can replace these forward models, which are basically based on based on physics. And so let's dive in how machine learning has transformed this field. And just to give you like a zoom out and brief introduction how these models work, basically they they try to predict the future by basically taking the state of the weather currently. So typically people use ERA5 to get their input state, so temperature, moisture, wind, and so on, and they try to predict the next step. And how they do it, they have some kind of a fancy neural network model that I'm not going to discuss today at all because I think it's not very important for this talk. And common features of this kind of machine learning based model that they take kind of large time steps compared to physically based models. So typically, let's say a few hours compared to several minutes. And basically given a state, they try to predict the state in a few hours, in 6 hours, and they can repeatedly basically step forward their models. I should say, since we're going to discuss a lot about what's online learning or end-to-end optimization, these models, one advantage of these pure machine learning models, that while trying to find this perfect neural network to predict the future, they can basically train over several time steps. What do I mean by that? Meaning that before this, so how machine learning works, we try basically to optimize to a set of weights or a set of parameters. And online learning or differentiable models allow us basically to take many time steps to again and again basically act with this fancy neural network, stop the model, let's say after 3 days or 4 days or 5 days, and ask the question, how would we change the parameters in order to optimize our prediction? So this is what is called differentiable. This is going to be important because this is partly of what I'll discuss later when I'll discuss our work and how we develop differentiable atmospheric model. But just to briefly, I think it's quite safe to state at this point that artificial intelligence revolution has arrived for weather prediction. So in this plot, you can see basically the skill relatively to the ECMWF IFS model, which is kind of the best existing physically based model versus time. Each dot is a different machine learning model, and you can see that basically they have been improving steadily. And once they cross the green line, they basically have a better skill than the IFS model, at least when we are measuring it by RMSE, but by root mean square error, which I'll mention a few limitations of that. But these kind of four models, Pangu, GraphCast, Fengwu, and Fuxi, are all basically outperforming the IFS model, at least when we are measuring it compared to RMSE. And but there are challenges with pure machine learning models, and I'll just highlight one of them and why it's a problem. So here we are seeing 8 basically panels. On the left, we're seeing basically data taken from ERA5. So this is what we are aiming to get. And on the right here, it's a machine learning model that tries to forecast it. So in the initial condition, they look pretty similar, but let's focus how the prediction looks after 72 hours. So beyond the fact that there are some errors, but this is like we can expect that, the main problem is that the right panel just qualitatively does not look like the left panel. You can see how small details, like little details, are basically smoothed out. So instead of having this kind of a lot of noisy patterns here, you can see that basically everything is smoothed out. So basically typically machine learning predictions leads to kind of blurry, longer, like blurry predictions at longer lead times. And this is a problem because we can think of several problems, but if we're thinking of probabilistic forecasting and producing ensembles, this is a problem because clearly it would be very difficult to create ensembles given that our predictions are smoothed out, and ensembles are, the goal of them are basically to give us a range of possibility of what are the possible weathers we're going to experience. In terms of climate, like even longer lead times of years and decades, this is a problem because basically what we want to model is the real atmosphere, not some kind of a proxy. And this, I think, for an expert at least, it would be very easy to determine which one is a model and which one is taken from data or a reanalysis data at least. And there is, I think, quite little hope that with models that tend to blur more and more with time, we can achieve reasonable climatology or simulations of climate. And so the next question I want to ask is why these pure ML approaches lead to blurry prediction? And one hypothesis, at least, that we kind of have had during the development of the project is because of their loss function they use. The loss function is what this basically machine learning models are trying to optimize. And typically what people try to optimize is what is called the mean square error, basically the difference between, let's say, ERA5 data and your prediction squared. And to understand why it is a problem to use such a loss function, let's look on this kind of a toy explanation. So we have the black line. We will consider it as the observation. And we have the blue line, which is our forecast. And you can think of this bump, say, as a tropical cyclone. And let's say the machine learning line now can produce two different forecasts. One would be putting this tropical cyclone here. So the shape is correct and maybe it's like the amplitude of wind is correct, but the location is slightly wrong. On the other option, it can just blur it out, like predict nothing. In terms of mean square error, the second forecast is more beneficial because it has less error. The upper, however, like the upper basically kind of like caricature is definitely the one we would like to get. We would like to get the information that might be a tropical cyclone. But so this is what is called in the literature the double penalty problem, that basically we're penalizing twice. Once for forecasting, like, let's say, large amplitude of wind, and second, because we put it in the wrong location, rather than just smoothing out everything. So this is one thing that we will try to avoid while developing this kind of neural GCM models, and I'll talk about it a bit more. I should mention that a pure machine learning model recently called GenCast have used a different loss function and succeeded to avoid this kind of like problem of blurring. But more broadly, if we're talking about like this kind of axis between pure physics models or almost pure physics models, like climate models and weather models, which on the one side try to basically by design, they are trying to generalize or designed to generalize. On the other end of the spectrum, I just talked about this pure machine learning models that are basically designed to predict short-term weather currently. And today, what I'm going to discuss is a set of different models, which are called hybrid models, which are somewhere in between these two. They want to take the kind of strength of like climate models in terms of they will rely on known physics. On the other hand, try to take the strength from like data-driven approach and learn from like this data that we have, like ERA5 or high resolution models and so on. And the hope is that one day maybe these models will serve us for climate. This is, I think, how they were born. But I will show also today that they can use for weather forecasting, and like with high skill, I mean, they can be used for weather forecasting. And so hybrid approach, in just one slide to explain the basic narrative. The narrative is the following. We have our general circulation model caricature on the right. And the idea here that instead of like relying our forecast on like inaccurate parameterization, that we will be able to somehow leverage high resolution models or observation to develop machine learning parameterizations. But we won't give up all the physics. We still want to incorporate the laws of physics where we can. Let's say a core, a dynamical core for our model also. If you think about the thermodynamics, fluid dynamics, and so on, at least the equations we can accurately solve, we want to still keep. But the parts that we are uncertain of, or at least they are introducing large errors to our model, we want to replace with a data-driven approach. And hybrid models have had kind of mixed success in the last few years. There are more and more of them. And I will just mention a few issues with these models that people have are basically that while developing they are discovering again and again. Many times this model lead to unstable simulations, so literally numerical instabilities. They try to incorporate somehow the neural network within a dynamical core or physics model or whatever, and they get unstable simulations. Sometimes they get climate drift over longer time scales. Where this approach mostly worked, I would say, is in some kind of idealized setting or learning from idealized models. But when we're talking about realistic setting with topography and realistic Earth, there has been, I would say, very modest improvements in models, like with hybrid modeling. And I will want to ask now why. And I'll give our answer, at least the hypothesis when we started this project. And the idea was that hybrid models typically optimize the wrong metric. And by the wrong metric, or what we call offline learning, I'll try to explain what do I mean by that. So how typically this hybrid model work is the following. We have some state of the atmosphere at time t, and we have some known state of the atmosphere that for the next time step, let's say 10 minutes or 5 minutes or 1 hour later. And the idea here is that we can operate with our physics model or a dynamical core and ask the question, okay, what do we need the machine learning to do in order to take us from xt to xt plus delta t? That sounds reasonable overall, but the problem is that we are training over a single time step. Basically, in this time step, we just every time we try to optimize the network is on a single time step, asking what's the missing physics here. And the problem is that in reality, this is not how models work. The models work like basically by progressively like running the model for more and more time steps. So when we train on a single time step, the neural network does not interact in any way with our physics. So you can imagine that once they try to we run inference for many time steps or a year or a decade, there might be problems. For example, there might be unstable modes that due to the interaction of the dynamical core with the neural network, they will give rise to unstable modes. Or let's think about conservation properties. It might be that in a single time step, we'll have a slight deviation from conservation of energy, and it will build up through time. But I think the best analogy I've heard, think about your car and your motor. If you try to tune your motor without putting it in the car, it probably won't work very well. So this was the kind of hypothesis when we started this project, that this is a problem, that we cannot basically optimize our network over longer time steps. But so this is where we start with our results. So I gave this introduction, trying to just briefly state where we stand in machine learning and weather forecasting and what is hybrid models. And I'll show you what the solutions we have tried to implement for this differentiable atmospheric model we have developed with, and we call neural GCM. So the goal, at least in the first part of the talk, is to build a hybrid model that is both competitive with pure machine learning models in terms of, let's say, root mean square error, but while not blurring this problem that I have mentioned. So basically, we would eventually want to get meaningful predictions. By meaningful, I say realistic atmospheric states that will allow us, let's say, to simulate ensemble prediction. And maybe if we solve these issues of blurring, maybe we could also make this model useful for climate. And so the two things we want to solve initially would be first, somehow to use online learning. I'll get into that again in the next slide, explaining the difference from offline learning. And the second thing is that find a loss function that would not kind of encourage our model to spit blurry results or blurry forecasts. So what's differentiable hybrid models? The differentiability means that we, instead of a typical dynamical core, which is written, let's say, in Fortran or even in Python, we have basically developed a dynamical core that is written in JAX. And what it allows us to do, it allows us, instead of optimize our prediction over a single time step, it allows us to optimize our prediction over many time steps. Namely, we can run our model for, let's say, a day or 2 days, and then stop the model and ask, how should we change the neural network weights in order to get a better prediction? In contrast, the offline learning was that we needed to do it over a single time step. So this was kind of the first thing we wanted to solve. So basically, while training, the neural network learns how to interact with our dynamical core. And so this part is what we got, that like the strength of machine learning models, like pure machine learning models, got that for free, I should say, this whole thing. But before we developed this code that allows us to have a differentiable dynamical core, we just couldn't do that. We could not ask after 2 days, how should we change the weights of the neural network to spit a better prediction after 2 days? So this is the first thing we have developed, and I'll try to describe the kind of like zoom out how we train our models. So we train it with ERA5 data, and the idea is the following. Our model is here. This is our dicore, and this is how our parameterization. You can think of a single column parameterization. And basically we want to plug as inputs the state from ERA5. Maybe we also plug in this forcing like SST, like sea surface temperature or sea ice extent. And we want to propagate our model. The problem is that the ERA5 model is on pressure levels, and our model works how we programmed it. Basically, it works on sigma levels. So there is one kind of gap here that I called here an encoder that basically takes the data from pressure levels, puts it on sigma levels. Then we propagate our models for as several time steps, typically several days. And then we have something we call a decoder that takes the basically fields from sigma levels to pressure levels. And then we can compare our prediction to ERA5 and optimize our model, basically. And just very briefly, what is this physics model that we learn, this parameterization we learn? Broadly speaking, it's very similar to like a conventional approach where we take a single column model, like basically the temperature profiles from a single column, moisture, winds, and so on, and try to predict the tendencies of the prognostic fields of our model, which are temperature, horizontal winds, and we have 3 water species, which is water vapor, ice, liquid, and liquid cloud, and ice cloud, basically. And so this is the structure of our model. So this is what was the first goal here, basically have some kind of a way that we could use our model for online training, running multiple time steps and optimize the weights of the network. And the second goal is to use a loss function which would not lead to blurry forecasts. And that took us a while to understand. And today I'm going to talk about 2 different types of models. One, which I will call deterministic, which just produce one basically forecast, and the other is stochastic model, which we will use for ensembles. So let's talk about the deterministic loss function we use. And we already saw the problem with using mean square error, and now I'll try to explain what we have done, the solutions we have found. So first, the realization. Here I'm plotting the error from the IFS model, so from physically based model, versus lead time, versus how many hours they try to predict for different wave numbers. So if you look at the blue one is like wave number 10, and the brown one is wave number 100. And what we see here is basically lower wave numbers are more predictable in time. That made us understand that basically working with a mean square error means that we are trying to demand our model to do something unrealistic. It's unrealistic to ask a model to predict after 10 days wave number, let's say 255. It's probably unrealistic because it's like very small scale feature, and we cannot predict this small scale feature over long time scales. So the solution we have found for that, we understood we need to somehow filter our target. We don't want anymore to get correctly the fields from ERA5 after, let's say, 5 days. We want to get something slightly different. What is this slightly different thing? Here I'm plotting what we are trying to, what is our target that we're telling our model to predict. After 12 hours, we have a lot of small scale features. Here I'm plotting just moisture. And the idea is that after 12 hours, we can still predict these small scale features correctly. This is what we believe. But let's say after 48 hours, we don't believe anymore we can get the small scale features. We do believe we can get the large scale features, let's say lower wave numbers. So the idea, we don't even ask our model to get correctly the high wave numbers after a certain time. So we are, as we prolong our forecast, we are demanding from our model to do different things. This is one realization. The second thing, we understood that we want to basically enforce that our spectral space, basically the spectrum would be correct. So we basically punish our model for not getting correctly the spectrum, even at high wave numbers. So this gives our model the flexibility to learn that it does not have to get correctly the high wave numbers because it's impossible practically, but we still demand it to have the right spectrum. So this is like zoom out, this kind of two tricks, what we thought, I mean, it took us a while to figure it out, but what we did in order to get sharper predictions. So let's see, this is overall what I'm gonna speak of our deterministic model, and I'll show a few of the results. So first of all, I will just say that we train models at different resolutions. So we first, of course, started with lower resolution that we can play with all these ideas, and it will be not very costly to train. And here basically the fields showing on the right is how the native grid of ERA5 is a quarter-degree resolution, and this is the model we train. So all of them are lower resolution compared to ERA5. And we use each one a bit differently, and I will talk. So first, let's look a bit about the results. So here I'm showing the RMSE, the error of our models. So here is geopotential, temperature, and specific humidity, and we compare it to what we call HRES. So this is basically the high resolution model from the IFS, of IFS. This is the dotted line. And what you can see, that neural GCM models, roughly at all resolutions, or at least at the two higher resolution, outperforms HRES. So this is what we were looking for. And the second thing I will just highlight that as we go to higher and higher resolution, our model becomes better, kind of similar to what you expect from physically based models. That you should go to higher resolution, it allows you a bit more flexibility in the modeling, and eventually it resolves more of the physics, you rely less on your parameterization, and you get a better model. And so this was the first step that we've done. We have kind of matched the existing machine learning methods just to be concrete. If we plot again the same plot from before that shows the skill relatively to the IFS model, this is our approach, neural GCM. This metric is slightly higher than these models, but I think it's not really important. What I think is important is the question, does neural GCM leads to blurry prediction? Because this would be already a qualitatively different thing it can provide compared to previous approaches. So to do that, let's just observe how our forecasts look like compared to ERA5, compared to the IFS model. And this neural GCM, at each model I'm writing here the resolution. And these are two basically GraphCast and Pangua machine learning based models. These are the forecasts after 1 day. I want to focus on let's look on the forecast after 5 days here. And let's look on the qualitative differences. You can see that although, let's say, Pangua and GraphCast are operating at the same resolution at ERA5, they have much less detail. This is this blurring that we have talked about. You can see that neural GCM, even though it's at a lower resolution compared to this model, it has more details compared to these models. It's still clearly not as detailed, let's say, as the IFS model, both because it operates like on a much lower resolution, but it is not obtaining a perfect spectrum still, but it is obtaining a spectrum that is not modified a lot with time. Namely, it's not blurring more and more with time, unlike, let's say, if you look at some of these models that with time they tend to blur more and more. These models, I mean the machine learning models. So basically, we have succeeded to develop this kind of model that both is competitive with these machine learning approaches and predicts and gives you a sharper prediction in a sense. This is what we were looking for. And so at this point, we were quite happy, but not completely happy for a few reasons. First of all, was that we have made these tricks with the loss functions that we were not really happy with. They were kind of ad hoc, that we learned incrementally and we had these ideas. But second, what we really wanted to provide is ensemble forecasting, be able to really sample from like different trajectories of the weather and basically conduct probabilistic forecasts. And to do probabilistic forecasts, so we need to create an ensemble of predictions. So we need some kind of a stochastic component in our model. So how we introduce stochasticity to this kind of model? This was a choice. It's not, there are other choices. The idea here is that we would provide some kind of noise to our parameterization. So from now on, we are not only providing the inputs from ERA5, we're not only providing maybe forcing like sea surface temperature, we also want to provide some kind of a noise. It's not not any noise. It's the idea was that we would learn what kind of noise is meaningful for this prediction. So what we do, we provide noise. We choose several Gaussian random fields, and we try to learn what kind of correlation length, both in space and in time, would be good to use. If you have, it's a bit similar to if you think about how SPPT works, how stochastic parameterization works. They provide some kind of a correlation length also. So the idea kind of came from there, or at least this was what we thought at the time. But the problem with this kind of approach is that we need a different loss function, because just providing some kind of noise to our model would not be useful, because our models would just learn to ignore completely the noise, because noise would not improve their mean square error prediction, for example. So how did we do that? What we did, that we completely modified our loss function. The idea is that we need some kind of stochastic loss function. In this case, we are using the continuous ranked probability score, or CRPS, as a loss function. And if you don't know it, it's fine. I'll give you like just a brief intuition of what it does. It has kind of two terms. One term encourages accuracy. Basically, it's the difference between your prediction and the ground truth. The second term encourages spread in prediction. Okay, from now on, this loss function demands us to produce at least two realization of our model. Because what it tries to do, it tries to increase the spread, the difference between realization 1 of neural GCM, here marked as X, and realization 2 of neural GCM, here marked as X prime. So basically, the first term just encourages accuracy. The second term encourages spread, which is kind of the opposite of blurring. Blurring is kind of, you cannot distinguish anymore between models. The tropical cyclones become just, let's say, very blurry. Here, it's the opposite. We really want to encourage kind of like different predictions. So this is what we use for our stochastic models. And these stochastic models already give us the opportunity to do something which I think is new, or say at least we are the first model to beat the ECMWF ensemble model. So what we are plotting here is the RMSE, the error of prediction, versus lead time. Let's start by focusing only on the orange plot, which is the IFS model, the deterministic model. And in gray, you can see here the ECMWF ensemble model. You can see that ensemble models, because they are kind of averaging over many realizations, they have much better skill than deterministic model, at least, let's say, at lead times above, let's say, 3 or 4 days. And what we have, and you can see here in green GraphCast, so purely machine learning approach. So it beats definitely ECMWF HRES model, but it does not outperform ECMWF ensemble. But neural GCM, our approach with the stochastic model, what you can see is that we are outperforming ECMWF ensemble, at least on most metrics, or almost all metrics, I would say. Just for completeness, I will plot here the CRPS, which is how typically probabilistic models are evaluated against, and not RMSE. And you can see also there we are basically outperforming ECMWF. And the next question I want to raise is, so does this neural GCM really produce a useful ensemble? Does it produce a realistic ensemble that has the variability that we can learn from, or we can use it for forecasting, let's say, tropical cyclone trajectories? And here I want to do some audience quiz. So here I'm plotting 15 days prediction from our model. So two of these plots are just showing a different realization of neural GCM model, and one realization shows era 5. I will give you maybe 30 seconds to look at it and try to each one guess, if you can like try to guess which one is era 5 and which ones are these two realizations from our neural GCM model.
Gassing the audience?
C.
We have a lot of C's and some B's.
Okay.
Okay, I can make it a bit even slightly easier. Probably here you will already be able to see some kind of differences already across the options. And I think I assume when you say C, you mean that it's like era 5 is C. And you're right. So definitely we're not, maybe we don't have a perfect model to mimic Euro 5, but I think we are on the way there. It's not very, like this was like 5 days prediction, and you can see the differences mostly in the tropics, I would say, that you can see maybe like that our realization does not capture as well maybe convective storms or something like that. But basically, I would argue, so most of you did predict that it's option C is ERA5, which is correct. But the point is that I would say that we have something that is getting closer to be kind of like that. I don't know if to call it exactly a Turing test here or something like that. That soon we will pass, I think, the Turing test, that it would be very difficult to guess which one is like the atmospheric, like ERA5, and which one comes from a model. And just to give an example, what we can do is this kind of like probabilistic forecasting. Here we took Hurricane Laura, so this is the black trajectory, and we try to produce an ensemble for the trajectories of Hurricane Laura. So the left one is taken from the ECMWF ensemble, and neural GCM is here on the right. I should say, of course, neural GCM is like I will get to it in a moment. It's much cheaper to run. It's much faster, so it has other advantages. But at least I think both of these kind of plots look overall similar, I would say. Okay, so let's go to the last section, where I want to discuss about the usage of neural GCM for simulations of like longer time scales, which I guess is the most interesting part, at least for some of you. And how we started is with like, I want to just start with like what we did. We basically, the configuration we work on is supplying boundary conditions, so sea surface temperature and sea ice extent, and also the total incidence of solar radiation, and try to run long trajectories. Was there a question? I'm not sure. No. Okay. So what I'm plotting here, I'm plotting the global mean temperature in the y-axis versus time on a year that our model have never seen before. It has never seen 2020. We've trained only until 2017. And what I'm showing here on orange, I'm showing ERA5 data. On green, I'm showing climatology from 1990 till 2020, which is clearly lower than the ERA5 just because of warming. And in light blue, the spaghetti plot shows our 37 realization of this trajectory, that they were all initialized during 2019. And you can see and the thick blue line is the mean of our predictions. And what you can see, I think, is that our model has roughly the right variability. It predicts pretty good like mean temperature, like if you're looking just the mean of our ensemble. And we were pretty encouraged by that. So we can run like 2-year simulation. And it's not only that we get correctly the global mean temperature. If we look at other things, we wanted to compare for like, let's say, the state-of-the-art physics-based model. Here we took the X shields with a 3-kilometer grid spacing model. So it's a global cloud resolving model that will run for 15 months. And we try to compare biases in neural GCM, the upper plot here, color showing biases of precipitable water, and in X shields. And what we found that our model has less bias, like here in pretty large factor, I would say. And also we found that, so if X shields is kind of the best physics-based model, we also compare to climatology, which you can think of maybe the best statistical guess if you know nothing. We also beat climatology. This does not happen only in precipitable water. We looked at several fields, but the most important part is to remember that our model can simulate 70,000 simulation day per day. and on a single TPU, which costs roughly $1 an hour. The X Shields can simulate 19 simulation days per day, and it uses over 13,000 CPU cores. So this is quite a big difference, I would say. And just as a side comment, we have done it for several fields, and we more or less find it consistent that our model has lower bias compared to X Shields, with the caveat that we were trained on ERA5, and X Shield, of course, was not. But clearly, it would be very difficult to train X Shield to produce ERA5 data. I have a couple of more minutes. I will just mention it briefly that we try to look on tropical cyclone. So here we look at ERA5 trajectory. So this is basically each dot is the number of times like a tropical cyclone has passed in each grid point, and this is how it looks for neural GCM. It's not a 34-year simulation, it's 34 realizations of specific year. It's slightly different, but you can see that overall it's the same. Like, and we can even divide it per like basin, and we can see that overall we think that neural GCM is doing a decent job in at least simulating tropical cyclone trajectory and numbers. But the last question before I end, we wanted to ask you whether neural GCM can run for even longer simulations, so AMIP-like runs, like really 40-year runs, and try to predict and predict correctly, let's say, global warming signal or something like that. And just to start with, that we have some issues with our model. I haven't talked a lot about them today. We still have many issues. One of them is sometimes we still get instability. So I'll just give you an example. Here on the y-axis shows the global mean temperature, the x-axis shows time, and this is like 40 years roughly, and you can see orange shows ERA5 data, that basically you see the seasonal cycle, and broadly speaking, our model, like neural GCM, follows ERA5, like the same trajectory, but at some point it just diverges. This is instability. The second thing can happen in our models that we have climate drift. So here, simulating 40 years again, you can see that slowly the blue basically trajectory is separating from the orange one. So we have a climate drift. This is not good. But sometimes, and the truth is that we don't know how to control it, we do get models that don't behave like that, that they don't have a climate drift, they have instabilities, but much more rarely, and they can simulate 40 years. Here, this is an example. This is just the global mean temperature over 40 years. It's very difficult to see, so I just zooming in and showing how it looks like after like almost 40 years of simulation. We are still following the global mean temperature. And to do that more like systematically, here I'm showing 22 realization of one of our models that happen to be more stable. And these are shown in the thin blue lines, and the thick blue line is our basically the mean of these 22 realizations. On purple, I'm showing 22 CMIP6 models from AMIP configuration. So it's AMIP models average over 22 models average, different models. On the orange line, I'm showing ERA5. The point is that we're doing pretty good. The correlation in the signal clearly comes from SST. So this is 1998, like the El Nino event. But so there is a strong correlation across all models. But the point is that we're doing a pretty good job, I would say, in simulating that. And the advantage, I think, of neural GCM that it could get, possibly at least, could get rid of certain like pretty persistent biases in climate models. So here I'm going to show one. Here I'm plotting tropical temperature trends as a function of pressure. And the x-axis showing the trend. The orange line shows you how ERA5 data, basically trends calculating from ERA5 data. The black dots are from like raw observations from the RAUB core. So this is basically what we are aiming for. You can see that the purple models, which are CMIP6 models running AMIP configuration, are basically overestimating the warming in the upper troposphere. And the black line are showing kind of the 25th to 75th percentile of models. So like half of the models, this is their range. The blue dots are showing what happened in neural GCM models, when again, this gray bar showing kind of the uncertainty. The point is that all neural GCM simulations are kind of similar to what happens in ERA5 data. Maybe it's not surprising given that we learned from ERA5, but the point is that neural GCM is not like, basically, it's less susceptible to the same errors that conventional models are doing, let's say, that are assuming something in their convection scheme. So I'll try to basically sum it up so we will have time for questions. So what I've shown you that we've developed differentiable hybrid model, and we can get state-of-the-art weather prediction. I didn't talk too much about physical consistency. Well, I should have deleted this point, but I would be happy to kind of discuss later. We can produce meaningful ensemble forecasts that outperform, or at least similar to similar to the ECMWF ensemble forecast. We can do longer integration, and we can sometimes even succeed to do AMIP like decadal simulations. And yeah, I would end here and would be happy to get any questions.
Okay, we have plenty of time for any questions in the audience? Okay, we have a hand. Dan? Yeah, just go ahead.
Okay, thanks for a really nice presentation. I wonder, with this tool, I feel like ensemble forecasts, evolved because we have these chaotic models, and that was a way of kind of plumbing what we're really after, which is kind of the joint probability distribution of future forecast states. I wonder with this machinery, is that something that you could go after explicitly rather than, thinking about one ensemble at a time?
So I don't think we are thinking, like, I'm not sure why you are saying, I might be missing your question, I should say, but CRPS is what is typically called the proper scoring, it's a proper scoring rule. So I think it aims to get the right distribution. I mean, this is a kind of simplification of expression of what CRPS is after for. I should say, regardless, that I should give a comment that I've said like relatively briefly, that there is a pure machine learning method nowadays, which just came out their paper in archive, which is called GenCast, that basically also taking a slightly different approach in diffusion models to produce the probabilities, but basically using also allow them to simulate ensemble forecasts. But maybe I'm missing why you are saying we are looking at ensemble member, I'm missing something, I think. So the second term here, I should say, is basically what basically encourages the spread. We are not thinking about maybe rephrase. I don't know. I'm probably missing your question.
Yeah, I'd happy to revisit. I think, if there's another tool that's really trying to solve for the joint distribution, then I can take a look for that as well. Maybe it's a different way of framing the problem.
Okay, we have Ala first, and then we have Judith, and then Okay, we have a lot of questions. But Ala, go first.
Yeah, thanks for the great talk. My question was on this slide, and how do you know what spread you're aiming for with this?
So, I mean, we didn't invent CRPS. This is what, again, this is what is called a proper scoring rule. So it's how it is designed. It is designed basically according to some set of laws that gives you what you are looking for. But basically, the aim of here is that the uncertainty will be similar to the spread. This is how it is designed. That if you train your model and you find that the RMSE of your model is not similar to the spread of your models, you've done something probably not correctly. So it is designed that, I don't know, so I'll just repeat it once more, that the variability across your ensemble members should be similar to the error. This is calibrated. It is a calibrated, maybe I can show an additional thing here, that our models are calibrated. And what do I mean by calibrated? Is probably put it in the end, is that their spread skill ratio, can you see this slide at the moment?
Yes.
Their spread skill ratio is roughly 1. This is a calibrated model. So the black one is ECMWF ensemble, the blue one is our model. You see we are slightly over spread. But if you look at different, realistically, this is not a global metric. You should look at where you we put it in the paper, where you have too much spread and where you have too little spread. But basically, calibrated models should have the spread skill ratio should be 1, and I would say we are roughly calibrated, at least when you compare to previous approaches that were under dispersed, that usually they have way too low spread skill ratio.
More questions. Well, 1, 2, 3, 4. Okay, we go with maybe Judith, and then Will and Peter, and then okay.
Yeah, thank you so much, Janni. First of all, this is really impressive. I was whispering, well, everything I worked on for years, you've just done in one paper. But I actually had the same thought that might relate to Dan's talk. And this is, I think, what we want to do in ensemble forecasting. We really want to do, and this is extended range, medium range, not the climate problem. Is we really want to solve the Liouville equation, right? Which is the change of probability distribution in high dimensional space with lead time. And so when we went to these traditional ensemble forecasts, we have one ensemble and we want to use it to look at extreme events and regional precipitation, and we also look at the ensemble mean and the spread. But I think what machine learning would offer is you can have one model for extreme events, you can have one model for extended range prediction. And there, a few years ago, SMWF was dropping resolution with increasing lead time. And the argument was, well, 3 weeks out, we cannot resolve these scales anyway. So in a way, you might be able to already do, basically predict some of the spatial temporal averaged PDF. And so if I would have started with this, I would have thought the same thing. Maybe, for example, subseasonal predictive skill, typically you only have skill if you average over 2 weeks. So could you actually look at the predictable skills and in space, time, and then write a machine learning model for those skills, which then would already do some of this spatial temporal averaging. Now, interestingly, you actually did exactly that, but you didn't put it into your forecast model, you put it into your metric. So I thought that was quite interesting. And I don't know to which degree is agreeing with Dan's point, but when I would want to have a predictive model for 2-meter temperature in week 3, 4, right, is a way to predict that and its spread, obviously, and higher order moments by just looking at the statistics of the PDF, or are you generating ensemble, which doesn't drop resolution and accuracy and then average over it? So this is an interesting problem, and I think you will contribute to that in the future.
I will just give a comment that I think there are quite a few people who are trying the approach that we didn't take, the directly predicting something like what you have described, let's say the mean and not really trying to have a mechanistic model that predicts the whole field, but predicting what you have described. But yeah, I don't think that we know what will work best. I mean, I think it's already almost surprising that this approach that we took, that basically we train our model over roughly 3 to 5 days, is eventually giving us pretty good skill over several decades, I would say. But yeah, it's definitely possible that there are more direct approaches to do that. I should say that we are entering now in our team this kind of mode, like to improve S2S prediction, and we'll maybe have a better answer after we have gained a bit of experience on what we can improve or if we can improve anything.
Okay. Yeah, go ahead.
Hey, Janni, great talk. Judith commented on a lot of things I wanted to bring up, but so I just have a simple question for you. When you're using your CRPS, did you freeze the model weights and you're just adjusting the length scale in the noise, or are you updating the entire model?
We do it to the entire model. At some point, what we did actually, I'll just go to the CRPS. What we did is actually in the beginning not try to learn anything about the correlation length. We are freezing it just for the initial part of the training, because otherwise some of the correlation length from our experience grew. But we are not. I should say that one of the disadvantages, we are controlling so many things that we cannot really do these ablation tests for like the number of things that we are changing. So many of the things that we have changed came from some kind of intuition or some understanding that we need to change them, but we definitely have not tested what you are suggesting or implying that maybe first tune your model and then try to tune the correlation length. We do it together.
Yeah, I'm just,
They have different, I should say they have different learning rates and stuff like that. We are treating them a bit differently, but.
Yeah, but so are you still doing the spectral matching in conjunction with the CRPS, or are you able to do that?
So we have several models, but yeah, partly we are using also CRPS. We are using what is called energy score. And I haven't talked about that. We are matching, sometimes we are doing two things. We are both trying to match over so if we go back to here, we are encouraging consistency by both trying to predict here correctly, but also we have a loss that acts in our model space as well. So this is like basically making sure that this model space, which is kind of like hidden from most people unless you really want to look at it, is being like we keep it that we understand what's going on there, that it's really we describe this kind of thing that we go from pressure levels to sigma coordinates, but the question whether is it really a sigma coordinates model? So we kind of we put a loss there to verify that we understand what's going on also there, which helps it to be a bit more physically consistent. I don't know if it answered your question.
Yeah, thanks, Janni.
Okay, we still have like a few minutes. Peter, do you still want to ask a question?
Yeah, just curious, when you run your machine learning model on longer timescales, have you looked at extreme events of, for example, what the PDF of precip looks like compared to the physical?
Yeah, I can show that. I should say that this is what I'm going to show is that the deterministic model, the stochastic model looks differently. It has much better extremes. 1 second, I need to remember where did I plug that. So, okay, yeah. So I should just say one word. We don't have precipitation. We have precipitation minus evaporation because basically we diagnose it. We don't predict precipitation. We just ask ourselves, like basically we are looking at the water budget, and since all the dynamics, the DICOR is taking care of like the horizontal advection, we just ask, okay, how much water was like added or subtracted from this field? And if you want to look at distributions, you can see them here on the left. So in the extratropics, we have GCM ERA 5 that it looks pretty well. In the tropics, we are underestimating extremes. The reason that we have never optimized to predict precipitation, and the reason is that basically what we are doing now is trying to learn directly from observations, and we thought that in any case we don't want to match ERA 5 distribution, so we have never even put loss on precipitation. We did not try to tell the model to get it correctly. This is just a diagnostic field in our thing, but we don't get it correctly. You can see that we are underestimating it this is tropical region, this is extratropics.
Thank you.
Okay, one last question. Yeah.
Is that me?
Yeah.
Thanks for the talk. Quick question, since we're almost out of time. You mentioned seasonal drift. I think this may be a bigger or more challenging problem than the blurriness issue, and I wonder what kind of strategies you may be using to tackle that.
You mean climate drift? I mean, I should say the drift in our model, typically it happens on the decadal time scale. Let's say like a few points of degree on several decades. This is the drift that we're talking about. So it does not like on a 1 year time scale. I don't think we can notice any drift, honestly. But yeah, we have a drift, like what I said, on a much longer time scales. I mean, you could see it as an example here. This is 40 years, and you can see maybe it drifts in these 40 years, I mean, maybe a degree or something like that, half a degree. And it's a problem. In practice, in theory, you could like think of all sorts of solutions, from energy fixers to stuff like that. Realistically, we don't have we don't have an operation, or like we don't have currently a solution to that. And the even kind of the worst truth, we don't know which models are going to drift. I mean, we train the models, and sometimes they drift and sometimes they're not. We don't have a way to tell you without doing this experiment, in a sense, whether they will drift or not. But they do drift much less if you look at like other papers before, when we are talking when within a few days, let's say the tropics got dry, it's a very different type of drift, I would say, but still definitely a problem if we're looking on climate modeling. We are missing many components clearly to do climate modeling, right? We need a coupled model, but we are on our way to think what we would actually need, but we are very far away from there.
Thanks.
Okay, all right, let's thank Janni again. Thank you so much. If you have other questions, just email Janni. Yes.